Okay, I welcome you on the BIMS Integrable Seminar. Today we have a talk from Maria Matushko from Miraz, from Moscow. With the title, Trigonometric Solution of Associative Yang-Baxter equation related to the queer-Lie algebra. And you have 1 hour.
Yes, thank you very much for the invitation. And I will start with the associative Yang-Baxter equation. So let A be an associative algebra and R is a meromorphic function of two complex variables taken value in this space. Not to do this, okay. The associative Yang-Baxter equation is the following equation that we have here. The equation is written in the tensor product of three spaces, and this is the associative Yang-Baxter equation. So it was introduced in papers by Fomin Kirillov in 1999, by Aguiar in 2001, and Polishuk in 2002. So, and it is called the associative Yang-Baxter equation. So the main example of the solution of this associative Yang-Baxter equation is the following. So let this associative algebra be this one. So, and P is the permutation operator. And the rational quantum R matrix, it is also called Yang R matrix. Here we have identity operator and the permutation operator. This sum, this is the example of the solution of the associative Yang-Baxter equation, rational example. So another way to think about this associative Yang-Baxter equation is as a generalization of the so-called Fay identity. So this Fay identity that you can see here is the identity that you usually know from, for example, integrability of Calogero-Moser system and like this. So you can see this to prove some things about integrable system. And the solution of this Fay identity is the following. So in the most general case, elliptic case, it's this elliptic function. Here we have an odd Riemann theta function. And in trigonometric limit, this solution reduced to the sum of cotangencies, and in rational case, it's just like this. And you can think about this associative Yang-Baxter equation as the matrix generalization of this Fay identity. And another solution of the associative Yang-Baxter equation, some basic solution, is the elliptic Baxter-Belavin R matrix. I will show you this. So, but important thing that in some proper normalization, because here the normalization is important. In quantum Yang-Baxter, for example, it doesn't matter. So you can multiply by some function this R matrix. And I give you an example. So this is the elliptic Baxter-Belavin R matrix in case n equals 2. So you can write it in standard Pauli matrices. So here sigma the standard Pauli matrices. And phi are functions that you have seen on the previous slide. So this is the solution of that phi identity. And this R matrix in case n equals 2 is also called 6-vertex R matrix, and that you know about this, yes. And let us rewrite this associative Yang-Baxter equation. So we have the difference of parameters on the, we had the difference of parameters on the previous slide. And now we just have 2 parameters here. So we rewrite, and these U are spectral parameters, and these indices, upper indices are they play the role of the Planck constant. And if you put the dependence of spectral parameters is on the difference of spectral parameters, you obtain the associative Yang-Baxter equation from the previous slide. So here I just show that it doesn't depend on the difference of spectral parameters, but it's the same as on the first slide. So how to go to the classical Yang-Baxter equation from this associative Yang-Baxter equation? If we have some solution of the associative Yang-Baxter equation that is satisfies this skew symmetry property, and it has a Laurent expression near this H, like this. So then this R small is the antisymmetric solution of the classical Yang-Baxter equation that you can see here. And the proof is simple. You just expand this R and put in the associative Yang-Baxter equation, and the 0 power of H and X gives you this guy. And if you change the indices here and the variables, you obtain this. And then you, then you just, due to the skew symmetry of R capital, you have the antisymmetry of this R small and symmetry of M. So if you subtract them, you the right hand side will be 0 because this cancels, and you obtain the classical Yang-Baxter equation. So this is the way how to obtain the classical R matrix if we have these properties. Okay, and how to go to the quantum Yang-Baxter equation? If we have some solution of the associative Yang-Baxter equation and it's unitary, so we have this property, and this F is symmetric, so this is symmetry property, and R is also skew symmetric, then it's a solution of the quantum Yang-Baxter equation. So it's not so difficult to prove it, it's some exercise. But you can see that this associative Yang-Baxter equation is like some bridge between the classical one and the quantum Yang-Baxter equation. Okay. Oh, sorry, this is not this presence. Sorry. Okay. Let us go to the supersymmetric case. Sorry, I have some another presentation. Don't know what. Can I just remove this and start with another one? Sorry. Because here not. I think it's not this. Sorry for this. And now I'm going to talk about the graded algebras and superalgebras. So if we have, so what is the superalgebra? A superalgebra is a two-graded algebra. So what does it mean? It means that we have A, and this is the sum. This is the direct sum of A0 plus A1 of these subspaces, and we have the following, that the following property, that this lies in this subspace, and it's Z2 graded here. And these elements from A0 are even, and this is odd elements here. And we called this degree of the element. Okay, and for the tensor product of superalgebras, the tensor product of this superalgebra is also a superalgebra. But with the induced Z2 grading. So the operation is defined like this. So now the multiplication is defined so it's the superalgebra with induced grading. And it's there is a natural way to define a bracket. So a bracket is defined like this. And for an associative superalgebra, we have the following important identity. And these two identities are the basis of definition of the superalgebra Lie. So the Lie superalgebra is the graded algebra, the two-graded algebra, with this operation with properties 1 and 2. Okay. And let us fix some notation. So in supersymmetric case, we consider this the two-graded vector space, this one, with a grading. So so 0 for I from 1 to n and 1 for another. And they denote by EIJ the generators of the Lie superalgebra. And the degree of them is just the sum of PI and PJ. So, and we regard this EIJ as the elementary matrix unit on this space. And as I have explained you in the previous slide, we can define the two-graded algebra as the tensor product with this multiplication. So it's just the definition of the tensor product superalgebra. So we fix the notation, and the first example of the graded R matrix, the solution of the associative Yang-Baxter equation is the following. Here we have identity operator and the permutation, but this permutation is just a graded permutation. So this is the formula for this. And let us check that this guy satisfies the associative Yang-Baxter equation. So if we so put this in the associative Yang-Baxter equation. So this is the lemma, and here is the proof. What we do. So we just write the associative Yang-Baxter equation for this guy. So we need to prove this. What we have? We have the first identity is 1 over x times 1 over y minus. And you can easily check that this is 0. So then if you multiply, for example, 1 over x on something with permutation, you have the same guy in another bracket. So this and this. And this type of things cancels. So we need to check only things with two permutations. So this we need to check. And why this is 0? Because P is the permutation operator. So we have these identities to the permutations. So you can use this, and you just use the Phi identity. So you use the Phi identity for this U. So you need to prove only without permutation these identities. And this is true. It's just the Phi identity in rational case. So the proof is very simple. We use only the properties of the permutation and some rational identities. Okay. And what is the trigonometric version of this graded solution? So this is the solution of the associative Yang-Baxter equation, supersymmetric in GLNM case. And we found this solution with other joint paper with Andrei Zotov, but I think it should be in the literature before, but we haven't found it. Because usually people use the supersymmetric R matrix UQ hat GLNM, and this is different. And this R matrix doesn't satisfy the associative Yang-Baxter equation. But these two solutions are connected by Drinfeld twist. So if we have this R beautiful, this is the R matrix of UQ GLNM, quantum R matrix. And this is the Zn extension of R matrix. So this satisfies, this in the left-hand side satisfies the associative Yang-Baxter equation. So the connection is the following. So by the connection can be done by the following twist transformation. But for our purpose with Andrei, we need the associative Yang-Baxter equation to obtain some quantum spin chains. And example. So this is the example for UQ hat GL2 and GL11. And you can see that here you have different things, and here also. And in case of this GL2, GL11, this is symmetric here, and this anti-symmetric. Okay. And this, why they use that type of R matrix? So this, in non-graded case, these trigonometric R matrices are limits from Baxter-Belavin. Trigonometric limit from Baxter-Belavin, from elliptic Baxter-Belavin. In non-graded case. And they satisfy the associative Yang-Baxter equation. Okay, let's go to the strangely superalgebra, queerly superalgebra. And now let the indices run from 1 to n and -1 to -n. These indices ij and ab are positive. And now we have the following grading on this vector space. So the grading is the following: 0 for the positive i's and 1 for the negative. And consider the following element. This element, this squared element gives minus identity, and the degree of this element is 1. So, and let us define the subalgebra of the subalgebra Qn, that is the centralized J. And you can check that is spanned by the following elements. So here A and B are positive from 1 to n. And this subalgebra is called as Lie superalgebra, the queer Lie superalgebra. You can also define it like, yes.
Can you explain what does it mean degree of J equal to the 1?
You have a degree of this EIJ, yes, and this is PI plus PJ, yes.
Okay, thank you.
Then here you have I degrees of 0, and for minus is 1, and it's a homogeneous element, yes, because in sum all things are degree of 1. Okay.
Thank you.
And you can define this queerly superalgebra as a fixed point of subalgebra in GLNN with respect to the following involutive automorphism. This so EIJ goes to E minus I minus J. So these definitions are the same. So the fixed points are given by the following elements. And this is the queer Lie superalgebra, the subalgebra of G, L, and N. And there is a quantum rational R matrix for this algebra, and it was introduced by Nazarov. Don't remember. Don't remember the 92 or 91. 92. Yes. And this is the formula for this. So the beginning is the same as the rational supersymmetric R matrix, and here we have this guy. And in components is the second line. So this involutive automorphism acts on this. So here you have E minus J minus I. And this is a solution of the quantum Yang-Baxter equation. And the main properties, it's unitary. So unitarity property, it's Q-symmetry, and it satisfies the associative Yang-Baxter equation. And this, I will show you how to obtain this property. So what we want to prove, we want to prove the associative Yang-Baxter equation for the queer Lie superalgebra, for the quantum R matrix of queer Lie superalgebra. So the formula for the R matrix is, so let us write it like this. So P capital is the permutation operator, And you can rewrite this from here. In terms of this J. J we had in the previous slide, but I remind you that this is the sum of these guys. And now we need to check the associative Yang-Baxter equation. So what we need to check? Proof of the associative Yang-Baxter equation. Okay. So we need to prove the following. So I just put this guy in the associative Yang-Baxter equation. Oh, sorry, this is not correct. Here we have 2 and 3. 2 and 3, not 1. 2, 2, 2, 2, 3. Here 1, 3. What I'm doing. And minus the last one. And it's not so difficult to prove this, so I will show you. So we need to prove this is 0. And we have already done this for the rational supersymmetric R matrix. So we did it for this, 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 this. And if we have, so we have the same, if we have some 1 over x, for example, times something with permutation, we have the same guy in another bracket, for example, 1 over x times this. And this cancels. So we need to prove only for 2 permutations, when we have some j's and 2 permutations. And for example, let us check the following identity. So G1, G2, P1, 2. So we choose the following guys. We choose this times this. I give that's in the square. We choose this times this. And we choose this times this. And we use the properties of G. So we want to show that G, that all the all things with permutation are equal up to a sign. So we just check that this guy, we want to reduce this. So using the property of permutation, for example, we put this permutation to the left. This G, they anti-commute. That's why we have here and the square of G is -1. Okay, we obtain this, and we can put this permutation to the right, for example. G2, G3, P1, 2, P2, 3. And using the permutation property, we obtain this. So what we have shown that this equals this, yes? And this P13, G1, G2, P1, 2 equals to minus G2, G3, P2, 3, P1, 3. So the numerators are equal up to a sign, and then we obtain the identity for rational functions, the Phi identity. And this is the proof. So you just check for all these things. It's not so difficult. That's why this satisfies the associative Yang-Baxter equation. So the natural question is, are there any trigonometric solution? And this is the trigonometric solution which satisfies the associative Yang-Baxter equation and related to the square-Lie superalgebra. So the structure is the following. You have the same guy as in trigonometric supersymmetric matrix, not the queer-Lie, this and this. And they are very similar with the next lines, because here this EII goes to E minus I, and this difference becomes the sum of parameters. So, and here is the same. This difference became the sum, and this. But this diagonal part where we have EII, EJJ, it's different a little bit. We have some models here, and it differs from the part of trigonometric solution of GLNN. And so I just found it looking to this trigonometric solution of the associative Yang-Baxter equation, and then try to do something similar with as in rational matrix that I have shown you, this automorphism, and the function depends on the sum of spectral parameters. And so I obtained this solution. Then Maxim Nazarov told me how to obtain in more clever way, and I will tell you. So let us start with the solution of the quantum Yang-Baxter equation related to the queerly superalgebra, but without a spectral parameter. And it was introduced, I think, in 92 also. Yes, in 92. So it was very fruitful year, and I was born. So this is the result of Grigory Alshansky, and it was in the context of Hecke-Clifford superalgebra representation and some super extension of Hecke algebra and the Sergeev-Shurveil duality. So he found this solution. So this is the quantum error matrix. So it satisfies the quantum Yang-Baxter equation, and it doesn't depend on spectral parameter. And this guy realized the representation of the super extension of the Hecke algebra. So this is so this super extension of Hecke algebra is some mix of Clifford and Hecke generators, and this S represent the Hecke generators, and this J that we have, GI, they represent the Clifford generators. So Clifford generators. So in this context, he obtained this result.
Who is J?
Okay.
Who is JI?
And JI, that guy that we have in queerly, it's...
You have J. Who is I?
I is, that is B. So you have the representation in tensor product of V. V, it's the number of the tensor component. Okay, I need to... So you have these guys, yes? And this J, A, act as identity, 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 and J in 8th place.
You say that you have in each side J such that each of them square equal to -1, but anti-commute is all other one.
Yes, they anti-commute. So J1, J2, they anti-commute. Yes. So it's like Clifford generators. So you have n these guys, or n-1. Yes, and they anti-commute. So this is the representation of Clifford part. And you know that the Hecke generators, they can represent it by the solution of the quantum Yang-Baxter equation, maybe braided Yang-Baxter equation. So yes, so you need to multiply by the permutation. But roughly speaking, it's like this. Okay. Andrei, are you happy? Okay. And then you can go to the affine Sergeev algebra, so affine version of this Hecke-Clifford superalgebra. And in this context, so we have this Heike generators, we have these Clifford generators, and then you can obtain some generators in affine, some elements in affine Sergeev algebra, where we have these spectral parameters which satisfies the braid relation. And in this way, we can obtain the R matrix with spectral parameters. So, and in our language is like this. So if you have the solution of the quantum Yang-Baxter equation, the squarely solution without spectral parameters, you do like this. So, and obtain the solution with spectral parameters. So it's like Baxterization procedure for this superalgebra case. But if you do like this R satisfies the quantum Yang-Baxter equation, but doesn't satisfy the associative Yang-Baxter equation. And you can transform this solution without spectral parameter. So if you regard this twist, so this F, it lies in the tensor product of queerly superalgebras, and this is the formula for this F, and you do this twist. So this S tilde satisfies the quantum Yang-Baxter equation, and it also satisfies the associative Yang-Baxter equation. And then if you do this procedure by Nazarov and Jones, you obtain the solution of the quantum Yang-Baxter equation and of the associative Yang-Baxter equation. And it is exactly the same that I have shown you, but they are connected by the gauge transformation. So this is this R matrix on this slide, and we can do the following transformation. And this is my R matrix from the slide with the big formula. Let's be the beautiful R. And the connection is the following. So this GU is this sum. And what we have this transformation, and it obviously doesn't how to say it. So it preserves the quantum Yang-Baxter equation, such transformations, and the associative Yang-Baxter equation. So this preserves. So transformation like this twist doesn't preserve the associative Yang-Baxter equation, but this preserves both. And so this is the way how obtain it from the solution with without spectral parameters. Yes, that's all for today. Thank you for your attention. I will be happy to answer the questions.
Any questions?
I have some questions because commonly if you have solutions to quantum Yang-Baxter equation, then some limit of the solution gives you what is called classical Yang-Baxter equation. And classical Yang-Baxter equation contains 6 terms, which is really sum of 2 associative Yang-Baxter equations.
Yes.
But there are many examples of solutions to quantum Yang-Baxter equation, such that corresponding local classical Yang-Baxter equation does not split. That means that you don't have obvious way to obtain solutions to the associative Yang-Baxter equation. Yes, and I just want to say that really many years ago, I and Sergei Fomin, I think introduced what is associative Yang-Baxter equation in abstract setup. And the known solution to the known systems like Below and Greenfield solutions and our solutions, they really satisfy not only the quantum Yang-Baxter equations, but they satisfy associative Yang-Baxter equation, which is really equivalent to the very, very special case of Fay-Trisicant identity.
Yes.
And some of because you use a certain notation which is a bit different from my notations, but anyway, for the super Lie algebra of type GLN and M, various way how to construct solutions to the associative Yang-Baxter equations. Yes, and again, it is basically it is analog or super analog of change relation between super transpositions.
Yes.
And I just wonder, do you have because commonly all this story related with construction of commuting family of differential operators, some analog of Calogero-Moser model, and so on. Do you have some version of Calogero-Moser operators for Quiva superalgebra?
I don't know about the queer superalgebra. There are some Calogero-Mosers for the GMN, MM case, but I don't about the queer case. I haven't heard about this. There are some papers by Sergeyev, Veselov, I think, Chilik, Fakin, with people about the supersymmetric Calogero operators. So.
Okay, maybe I will ask one more question, because in some sense, in the base of solutions to associative Yang-Baxter equation, it is some version of Fay-Trisicant identity. Do you know super analog of Fay-Trisicant identity?
No, I don't know. Is it exists? Is it does it exist? Do you know? So for these proofs, I just use the normal Fay identity, not supersymmetric. But it's interesting. Are there any super analog of this? So in some sense, it's not the generalization of some supersymmetric Fay identity, it's generalization of normal Fay identity. So it's but these R matrices, they act in the super symmetric spaces. I don't know.
Thank you for answering. Do we have questions from the Zoom? Probably not. So we thank the speaker again.
Yeah, thank you.
And thank you, other, for attention. See you next time.
Okay.